Hello everyone, welcome to Anubhav Intech. This is your fan guy, and today we are starting with our system design interview series, where I'll be teaching you system design and why do we need system design in the first place. So we would be learning why did engineers invent all these complicated things in the first place, right? And the goal is to understand why do we need system design and why does system break at scale? Okay, so imagine you have built a backend service for a startup that you're working in. You could be an intern, SD1, SD2, SD3, anyone who is watching this video. Imagine you launch this product whose architecture looks something like this. You have a client, you have a backend server, you have a database. You launch this product, you got 10 users signing up, very happy. Everything works perfectly. Now you have 100 users, still fine. Okay, 1,000 users, no problem. Still, the service is working fine and you're able to handle all the requests within your SLO or SLA, no problem. And then imagine one day a famous LinkedIn influencer like me
It is.
post about your product and your product goes viral, and within minutes your entire system crashes because now you have from 100 users to 100k into 1 million users, right? So this is the architecture that almost every startup begins with. Even when I was building my startup myjob.ai, even I started with this very simple architecture, right? One server, one database, simple, clean, and cheap. Easy to build. Easy to build in like 2 to 3 days or maybe within a month. For few hundred users, this will work perfectly, no problem. And that's important, right? A good system design is not about building for millions of users on day one. It's about knowing when will things start breaking. I mean, you know about your system beforehand. So when you had 10 users to 100 users, everything was working fine. I mean, it was still manageable, right? You might see surge in memory increases go up, but the system remains healthy and the response time would be still manageable, right? No major issue. And that's why engineer thinks that scaling is easy, right? Because what if I just throw more servers? I mean, what if I just instead of a machine which has two CPU cores and 4 GB RAM, I would throw up more. I mean, I would say, okay, now I'll upgrade it to an upper tier machine of 4 CPU core and 8 GB RAM. Then as soon as you hit your 100k user, the first bottleneck will appear. Now I want to you to pause the video and answer this. What do you think is the slowest component in this architecture? Client, backend server, and database. I think you have already answered it. If the answer is server, you're wrong. The answer is the database because the database is the real heart of this architecture because every request eventually becomes a CRUD operation. Select, insert, update, delete. So the database is doing the real work. And that's why your database is burning now. Your database has become bottleneck because your database can't scale further for these many users. Right? Now I know it's a bit early, but I want you to understand the concept of throughput. Just bear with me. If you haven't heard of the word throughput, I think you'll get fair idea. Throughput by definition is number of requests a system can process per second, right? So let's say your server is handling 100 requests per second and your database can handle 50 requests per second. Now the question is, what's the system throughput? Is it 100 requests or is it 50 requests that your database is able to handle? So imagine this as a 6 lane road versus 1 lane bridge. The bridge controls the traffic, not the roads, right? So your database is here the culprit, the problem, the bottleneck. Even though your server is able to handle double the request that database can, still the database is the bottleneck. So now at this point, many engineers will come and say, "Hey Anubhav, I'll add I'll add more CPU. I mean, if more users are growing, I'll add more CPU, right? So that my system scales. But still, your requests are getting right. I mean, anyway, all the requests which eventually transform into a database query, right? So you might need to also scale your database rather than just the backend server. If you don't, your backend server will also burn. Or let's say you have millions of users now, rather than just 100k users. Your product grows even further. You have millions of users now, and at this point, you have already scaled your database and backend server. But now let's say your database is receiving 1,000 queries per second, and the capacity is only 500 even after scaling, what happens? You will start seeing request failing. You will see out of memory errors. You will see connection getting lost of your database. The very common problem is database connection timeout. Or you will see service is unavailable. Your backend service is unavailable because now it has even more number of requests to pass through. So one would say, hey, Anubhav, just buy a bigger server, not even bigger server. I mean, we know we scaled our backend server when we had 100K of user. Now, still one might say, hey, Anubhav, scale even further, buy a bigger server. Like now we can talk about this term called vertical scaling. I mean, we just had this word. So vertical scaling is very simple. Imagine you had 4 CPU. Now you vertically scale to give it 8 CPU, 16 CPU, 32 CPU. I mean, you can go like crazy, right? But that takes good amount of money from your pocket. But as a startup, initially you don't have this much budget. So I mean, even though if you have good budget, you will be able to do vertical scaling, and then limit appears. Okay, the cost of your architecture, your product, tech cost will explode, right? Now you can't even go beyond certain point. Now then the questions come, Anubhav. I think we can't even scale further. I mean, vertically scale further. Then instead of scaling up, why don't we scale out? I mean, instead of scaling vertically, why don't we add more machines to it? Right? If you don't do this, your your clients will be very unhappy because now they are seeing increased latency in the response time. I mean, the response time is bad now. They might be waiting for seconds, like 5 seconds, 10 seconds, 15 seconds, even for a simple get query, right? So here was the birth of system design, right? Now you can connect everything. Why did we need? I mean, this is a very simple or very uncomplicated way of explaining things. Now we can connect everything. Now every famous system design component exists because something is broken. To fix that, we need something. Now, let's say your server is overloaded. You would need some load balancer because now you have multiple servers. I mean, we just discussed that instead of doing vertical scaling, we will be doing horizontal scaling. I mean, scale out. Then you would need a load balancer which can actually divert the traffic to your nodes. I mean, to your machines. Let's say your DB is overloaded. You'll create replications of database. I mean, you could have one single, let's say if your system is write heavy, a lots of request is going to your database, which is mostly write. I mean, you're writing something, not getting something. I mean, it's mostly insert and update commands. Then you might need to think of a database where we have a global database, which is your write server, where you do all the writes, and you have multiple other database which are like replicas of this. This is called master slave architecture, where you have one master database which handles all the writes, and then all these writes gets propagated. I mean, all these snapshot of their database gets propagated to your read replicas, and all the read queries happens through these replicas, right? And let's say if we have some repetitive reads, repetitive as in, let's say a particular request is coming a lot more time, right? You can cache that. Then the caching logic comes into the picture. You must have heard about this term redis. Redis is like distributed memory cache in memcache, right? You can have an in-memory cache, or you can have a distributed cache, a cache where you can store all those hot queries. Hot queries, I mean, a queries which is appearing quite common. So when you have too much of data in your database, you will think of sharding. Okay, why not let's simply divide our database into multiple shards, and instead of scanning the whole database for a read query, I'll decide for this particular query which shard I should look for. A very simple idea could be geoparticle sharding. I mean, imagine a request which is coming from India. Instead of having a huge database which stores information for all countries, I mean, across all the regions, you will only look through the shard which stores the data of India. A very vague analogy or very vague term. Or let's say single point failure. I mean, a single machine, a single core server. Then you would talk about distributed system, right? You would say I'll add multiple such servers, multiple such instances of this system into different regions. Now this thing would be much clear. So system design is not about memorizing these concepts. This should come intuitively once you understand the system, what is breaking and what can be applied to fix it. Like we just discussed, right? So it's not about memorizing message queue like Kafka, Redis, load balancer, API gateway. No, system design is a study of what breaks your system when it grows, right? So in this code, we'll start with very simple architecture and we'll gradually fix every bottleneck until it handles millions of users. Perfect. So we'll meet in the next video where we'll be kicking off with the actual system design fundamentals that will be very important as a knowledge. I mean, you should have it in your head all the time so that it will help you while designing, while doing system design interviews. So I hope this was an easy way of learning why system break at scale and why we need system design in the first place. Thank you so much for watching. Bye bye.